In this video, I'm going to be talking about another approach for fewshot learning, which is in the context of meta-learning, but we are using the contrastive idea for partially observed data. So I'm going to be focusing on this paper on 2023. Many contrastive and meta-learning approaches learn representations by identifying common features in multiple views. However, the formalism for these approaches generally assume features to be shared across views to be captured coherently. We consider the problem of learning a unified representation from partial observations where useful features may be present in only some of the views. We approach this through a probabilistic framework enabling views to map to representations with different levels of uncertainty in different components. These views can then be integrated with one another through marginalization over that uncertainty. Their approach POEM enables us to meta-learn consistent representations from partial observations. We evaluate our approach on an adaptation of a comprehensive fewshot learning benchmark metadataset and demonstrate the benefits of that over other meta-learning methods at representation learning from partial observations. So this is the standard contrastive learners that minimizes the relative distance between the representations. And this encourages the learning of features that are consistent in all views. In the above example, this corresponds to the pattern on birds' wings. To better handle partial observability, where features may be disjoint between views, we propose partial observation experts modeling. And it instead maximizes consistency between multiple views by utilizing representation uncertainty to learn which features of the entity are captured by a view, and then combining these representations together by weighting features by their uncertainty via a product of experts model. Factor analysis is the linear counterpart to model representation learners, but where partial observability is inherently expressed in the model. The inferential model for the latent space in factor analysis is a product of each of the conditional Gaussian factors. In general, this form of inferential model can be captured in the work of Hinton. Let us consider data corresponding to partial observations. So in common with most fewshot learning, we arrange the data into support set and query sets. Each support consists of m data items, and the m's item collects views where v may vary with m. So the items in the support set are sampled randomly from the training dataset. And the query point consists of a single different view corresponding to one and only one of the m items in the support set. So we are concerned with the partial observability, that is, not every data view will inform the whole representation. So instead of mapping each view to a deterministic point representation, we map each view to a distributional representation where each component is just a normalized density that indicates the uncertainty that component, or we call it factor. We denote this conditional density and on implementation And an implementation parameterizes the parameters of the distribution with the neural network. So we combine the corresponding factors for each view together using a product of experts. So we compute a product of expert distribution for representation Zm. And P of Z is a prior density over the latent space. Now, for a query point with a view that matches other views from example data item M, we can use the Bayes rule to compute the probability that the query point may be generated from the corresponding representation. And then after combining them, the marginal predictive P of X star is used to form the training objective. So we wish to maximize the likelihood for the correct match of query point to support set accumulated across all support and query selections. So while the normalized factors can be chosen from any distribution class, we take phi to be Gaussian. And if the representations from each view up for a support point are aligned with each other in the query view, they will have a great overlap, and the integral of the resulting product of Gaussians will be larger, leading to a greater value of lambda. While the numerator of 4, the numerator quantifies the overlap of the support set with the query, the denominator contrasts this with the overlap of support set representation with the prior. Together, this factor is enhanced if it is beneficial in overlap terms to replace the prior with the query representation, reduced if such a replacement is detrimental. So this is a standard fewshot learning which requires the prediction of an image from a sample. But our adapted task evaluates representation learning under partial observability by instead requiring prediction of the underlying image from partial views. And views are generated from the standard contrastive augmentations. We use stronger cropping because you can do cropping for data augmentation in different ways. And we can compare this model with the Protonet, and you see that it has a better performance. And the PyTorch code for this, of course, is a pseudocode